Hi, welcome to Pre-AP Physics Accelerated Motion. This is section 1.3. Acceleration. Velocity is not always going to be constant. Sometimes you speed up, sometimes you slow down. That's acceleration. When velocity changes over time, this is acceleration. The average acceleration. If acceleration is constant, the acceleration calculated will actually be the average acceleration. This is the only kind of acceleration we are going to deal with in this class. Instantaneous acceleration is defined as the acceleration at any given moment. So when we find our average acceleration, we're also finding the instantaneous acceleration. All right, remember you have three basic kinematics. Kinematic 1, v is equal to v naught plus at. Kinematic 2, x is equal to x naught plus v naught t plus 1/2 at squared. And kinematic 3 is v squared is equal to v naught squared plus 2a x minus x naught. You also have three graphs. You have an xt graph, which is a position time graph. This is going to be a curve. You have a VT graph, that's a velocity time graph. This will be a sloped line. And now you have an AT graph for the acceleration. Okay, this will be a flat line showing that constant acceleration. Graph transitions. The slope of an XT graph is equal to the velocity. The slope of a VT graph is equal to the acceleration. The area under a VT graph is the displacement, and the area under an AT graph is the change in velocity. Example 1. A ball is pushed with an initial velocity of 4 meters per second. The ball rolls down a hill with a constant acceleration of 1.6 meters per second squared. The ball reaches the bottom of the hill in 8 seconds. What is the ball's velocity at the bottom of the hill? We're going to start out by doing a TÜV chart. The first term we come to is velocity in meters per second. We know the v naught is 4. Acceleration is in meters per second squared, and it is 1.6. And time is given in seconds, and t is equal to 8. So let's do the EWAU. The equation that we use that involves all three of those variables is v is equal to v naught plus at, which is kinematic 1. Substituting in our values, v naught is 4, a is 1.6, and t is 8. Calculating, units, make sure the units always match, and they do. Answer in units, the velocity is 16.8 meters per second at the bottom of the hill. Example 2. Given the velocity time data below, what is the displacement of the object? Notice that you're given VT data. So since data is given, we're going to start with a VT graph. When we graph this velocity time data, okay, we're going to get something similar to this. Notice that I do only have 4 data points that were given, and I plotted those 4 data points and drew that line. Now let's look at finding our displacement. Remember, we have 2 ways to find displacement. One way is based on the area under that VT graph. So the equation for area would be a rectangle and a triangle. Okay. The triangle is 1/2 the base times the height, and the rectangle is length times width. We're getting these numbers from the graph and the shapes from the graph. On our graph, the base is the time and the height is the change in velocity. And the rectangle would be the velocity and the time. So substituting in all of the values that we know from the graph and calculating, we get 144 meters. Now that's one way to find it, is based on the area under the graph. The other way to find it is based on the equation of the graph itself. So the equation of the VT graph is v is equal to 12 plus 4t. We're going to use a default starting position of the origin, And our kinematic equation is the kinematic 2, x is equal to x naught plus v naught t plus 1/2 at squared. Substituting in all of the things that we know from the graph and the equation and what was given, we find the units do all match, and we do get the same answer of 144 meters. This is what you're going to be doing in 1.3, is calculating and solving these problems. Good luck. We'll see you next time. Thanks for watching.